from Gradeup, and we are here in the series of paper 1 material science is going on. And my dear, today we are going to see the line defect and surface defect, and we will be completing this subtopic crystal defect, which was very important topic, my dear. And the weightage of this topic is going to be minimum 2 questions basically from paper 1, and for mechanical student it will also be coming in technical also. Yes guys, please tell me, am I properly audible and visible to all of you or not? Please tell me that. Then we are starting the session. Yes. Yes guys. I am fine, Sajal. So you are very punctual. Very good. So you are taking care of paper 1 right now. That is a wonderful thing. Gaurav Vajpayee, good morning dear. So am I properly audible and visible to all of you? Yes. Okay, fine guys. So guys, our discussion is going to be related to the crystal defects. And my dear, when we are talking about crystal defects, we have already seen the point defect. A quick revision I am showing you for the previous class. Yes my dear. And as I already told you, the weightage of this subject, once again every day I am showing, so that you remain motivated for that. We already discussed about crystal imperfection, and I told you yesterday that imperfection means short range deviation. Long range deviation means amorphous. Short range deviation means it is imperfection. Dileep Singh, sorry for that dear. Actually this channel is for English only. For Hindi you can join our channel Gradeup Gate Mechanical Marvels. Their classes are going in Hindi, here classes are going in English only. Rishabh, good morning dear. GR Giri, hi dear. So yes guys, so we have seen short range deviation means imperfection, long range deviation means amorphous. Yes. So my dear, then I already told you that perfect crystalline material is 1000 times more stronger than the presently available material. So we have seen different types of defect yesterday, and I also told you, the point defect, vacancy, self-interstitiality, Frankel defect, impurity, and Schottky defect. Now we are going for line defect, surface defect, and volume defect. So my dear, I will be starting from line defect. Malai, good morning. How was your GATE exam? You came after so many days. Now don't miss the classes. Every day we are here for engineering services also. Randhir, hello dear. Bahut badhiya. Amit Kumar, good morning dear. So let us move to the line defect, my dear. Then I taught all these defects what are related to point defects. And now we are moving towards, my dear, the line defects. Yes. So let us see the line defect, my dear. So when we are talking about the line defects, line defects are also known as dislocations. They are also said to be the dislocations. And my dear, these are of two types. One is edge dislocation. My dear, other is a screw dislocation. Don't worry, I am having diagrams for all of them. But first of all, I am showing it manually. Then for feeling, I am showing the other diagram. So both the diagram I am showing to you guys. So don't worry about that. Yes. So guys, okay, fine, Malai. So as I said, my dear, these series are made for your benefits. And from Wednesday onward, we are launching a crash course for you guys for engineering services paper 1, as we have done for GATE also. And in paper 1, our entire team of Gradeup, those who are taking paper 1 subject will be in front of you, and they will be taking one by one all the subjects for you guys. I can guarantee your selection if you are attending this series. It is going to help you to get wonderful number of marks, a good weightage marks from paper 1. Okay. And there is no reliable source for paper 1 as far as other platforms are concerned. You will be getting something better, not better, I will say best here. So a little bit harder for me. I learned from GIT. Okay, no issue, Malai. So Gata Mukherjee, sir, what is the class number for today? Dear Sogata, today class number, if you are asking me, this is the 4th or 5th class. But don't worry, soon we are going to launch crash course. where we will be covering from Wednesday all the subjects. So don't worry. Okay, अमित कुमार सर GS के लिए भी कुछ करिए. डियर सभी all the subjects, सभी subjects पेपर 1 के कवर होंगे. All the subjects of paper 1 will be covered here. Don't worry. Thirumalai, hi dear. So my dear, when we are saying about edge dislocation, when we are saying about screw dislocation, they are said to be, my dear, they are said to be the line defects. So when we are talking about this, one name also is there is dislocation. So when we are saying edge dislocation and screw dislocation, for showing you, I am showing you a complete lattice. If you remember, I told you that we will be using the line lattice or space lattice. If you remember, when we see atoms like this is the complete parent metal lattice. If you see, if I show you the atoms like this, so I am going to show you the complete parent metal lattice. If you can feel, these are the atoms. Let us say these are the atoms of some materials. Okay, I am making these atoms. These are the atoms of some material. And my dear, just remember one thing. When I was teaching you, I told you that why line defects are coming in picture when point defect is present at more than one place together. Like if you feel this, my dear, there are point defect vacancy, point defect vacancy, point defect vacancy. So there are point defects present at more than one place. Okay, dear, it is not third class, it is the third session of crystal defects. I will say crystal structure I have already taken 3 to 4 session. I feel totally this is the 5th or 6th session. Okay, but don't worry, you will be able to get, don't worry. As I said, my dear, these are 3 vacancies. When a position is vacated by an atom, it is said to be a vacancy. So my dear, these are 3 vacancies. And if I show you this in terms of line lattice, I will be showing it like this. In terms of line lattice, I will be showing you like this. Like this. Like this. Like this. So I will be showing you the figures also, guys. I am having all the types of diagrams, but I am showing you manually first to give you some feel of the subject. So if you see, my dear, here, if you can feel here, there are vacancies. If you can see, my dear, this is a vacancy, this is a vacancy, this is a vacancy. So you can see 3 point defect existing together. Yes, Rinkesh, hello. So 3 point defects are existing together. When more than 1 point defect is coming at one place, it results into line defect. Okay? When more than 1 point defect is acting at one place, it results into line defect. So my dear, here 3 point defects vacancy are coming together. They will result into line defect, and that line defect is said to be dislocation. If you see this in the 3-dimensional view, it will be like this. In backside also the atoms will go like this. In backside also the atom will go like this. Like this, yes. Okay. Like this. In third dimension also the things will be there. Because a crystal structure is a 3-dimensional structure. That is for sure. So my dear, when we are going to talk about this, here 3 atoms are missing. So what will happen here, I would like to tell you that, my dear, basically for this atom and this atom, you can see the gap between these atoms is going to be more than bond length. Why? Because intermediate atom is going out because it is a vacancy form. So these 2 atoms, the gap between these 2 atoms is going to be more than the bond length. In the first class I told you, when the gap between 2 atoms is going to be more or less than the bond length, they will be having some kind of attractions or repulsion. I told you in 2 atoms there are nucleus, there are electrons. So nucleus is positively charged, electron is negatively charged. So my dear, what happened is positive charge of two nucleus repel each other. Negative charge of electron in two atom repel each other. But nucleus of one atom attracts electron of other, and electron of one atom attracts nucleus of other. So there are a number of attraction and repulsive forces are present between two atoms. So my dear, I already told you that whenever two atoms are coming closer to each other, their repulsion forces increases and attraction forces reduces. And whenever two atoms are going away from each other, the attraction between them increases and repulsion between them decreases. So my dear, that's why the gap becomes very important. And two atoms want to be at a distance where they are having neither attraction nor repulsion. That distance is known as the bond length distance. Dileep, I already told that dear, this is the rule that on this channel we cannot teach in Hindi. This channel is dedicated for the students who want to learn the things in English. Sorry Dileep, I can understand this, but as I said, in this channel we cannot teach in Hindi. For Hindi we are having a different channel, that is Gradeup Gate Mechanical Marvels. There we are teaching in Hindi. Okay, in this channel we need to teach in English because everybody do not understand the Hindi. The problem is that. Okay, so my dear, when we are talking about this, as you know that if this atom are far away, obviously, so as the distance between these two atoms will be more than the bond length distance, so my dear, obviously because of that, these two atoms will start attracting each other. So my dear, there will be attraction present between two atoms. So there will be attraction present between two atoms. So these two atoms will be attracted towards each other. And if due to this attraction, the same feeling will be there in these two atoms, the same will be there between these two atoms. And if these atoms are going to move, then obviously the gap between these two atoms will also increase. Between these two atoms will also increase. Between these two atoms will also increase. And they will also start a attraction force they will be having. So my dear, because of this, these atoms are going to move from their location. And जैसे हिंदी में बोला जाता है, जैसे आप बोलते हो कारवा चलता गया. So my dear, this thing will continue, and in that way these atoms will be having a tendency to move for sure. Okay, yes. Okay, fine Tirumalai. Rikesh sir, vacancy में bond क्यों नहीं दिखाते? Dear, because bond is between two atoms. Vacancy means empty space. How you can make bond with the empty space? Okay, like you always make the relation with the humans, with the pets, with the dogs. Have you make the relation with the empty space? No. Dear, with empty space you cannot make any relation. Bond is a kind of relation. Okay. So my dear, because of that, this movement will be there. So you can see, my dear, the group of atoms will start moving. So the movement of group of atom is said to be slip. My dear, the group of atom is said to be dislocation. Why dislocation? Because this group of atom is going to dislocate from its position. So it is said to be dislocation. And movement of dislocation is said to be slip. So my dear, I would like to say that the group of dislocated atoms from its position is said to be a dislocation. Okay, and movement of dislocation is said to be slip. Okay, my dear, and slip refers to the permanent deformation of atoms. Saugata sir, why attraction between atoms occurred? Didn't get properly. Dear Saugata, as I said, yes, Dileep Singh, this class is helpful for mechanical, civil, EC, EE, all the branches. My dear, in engineering services, paper 1 is common for all. And if you have not seen the previous classes, you can start it from the very first class. And these class, as I said, this today's session is going to give you 2 marks for sure. Because this chapter is coming for at least 2 questions. One question we have discussed the material yesterday. For one question we are discussing today. And in the next session I will be bringing some previous year's question of engineering services from your papers. So by looking at that, you will feel that whatever we have studied, how important it was. So Gata, yes, you can have one thing, that when two atoms are having nucleus is having positive charge, electron is having negative charge. So two nucleus repel each other as they are positive charge. Two electrons also repel each other as they are negatively same charge. But my dear, there is an attraction between nucleus of one atom and electron of other atom. There is an attraction between electron of one atom and nucleus of other atom. So there are a number of attraction and repulsion forces exist. So my dear, it has been found that whenever you take two atoms nearer to each other, their repulsion forces are becoming more than the attraction forces. And whenever two atoms are going far away from each other, their attraction forces becomes more than the repulsion forces. And at board length, attraction and repulsion becomes equal. So net is 0 and net potential energy is 0. And everybody wants to be at minimum potential energy state. Everybody wants to be at that. So Dilip, don't worry, whatever we are discussing here, it is for every branch, not for mechanical, not for civil only, for all the branches. Okay? Yes. Or paper 1 ke liye hai. This is for paper 1. So my dear, when we are talking about this kind of dislocation is said to be edge dislocation. Now the question is that how the question will be coming from this. First question is this: when more than one vacancy is present together, it will result into, you will say, edge dislocation. It will result into edge dislocation. And if in this edge dislocation you can feel whatever the motions are going on, are going on in the lower part. In upper part there is no change. So my dear, that is the reason upper part is said to be unslipped part. Upper part is said to be unslipped parts. It is said to be unslipped part. And my dear, lower part is said to be slipped part. Lower part is said to be slipped part. So upper part is unslipped part, lower part is slipped part. Because in lower part you can feel the motions of atoms. And my dear, this part is going to be slipped part. This upper part is unslipped part. So this is the part where slipping is going to take place. In the upper part there is no slipping. So my dear, I would like to say that this is the line which separates the slipped and unslipped part. This is the line which separates slipped and unslipped part. And this line is said to be dislocation line. Dislocation line. Dislocation line. And my dear, if you can feel the movement, this is the dislocation line, and the movement of atom is going on like this. The movement of atom is going on like this. The movement of atom is going on like this. So my dear, you can feel one thing, that the movement of atom is going to be perpendicular to the dislocation line. The movement of atom is going to be perpendicular to the dislocation line, and this movement of dislocation 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 is shown by Berger vector. Is shown by Berger vector. So Berger vector shows the direction of dislocation movement. And my dear, Berger vector is represented like this. What does this say? This indicates the partial plane of atom. This indicates the partial plane of atom which is present in the figure. And this is said to be, my dear, this is said to be the closely packed plane. Or you can also say this as a dislocation line. So my dear, if you see the previous figure, this is the partial plane of atom which is present. Okay, so for this we are showing Berger vector like this. Okay, so my dear, this is how Berger vector we show like this. Now my dear, the next question they will be asking the direction of velocity. So you will be saying the direction of velocity is perpendicular to the dislocation line. So the question will be that the direction of dislocation movement is perpendicular or parallel to the dislocation line. So it is always perpendicular to the dislocation line. This is another question which is asked. And my dear, when we are showing this as Berger vector, this is the representation, and this kind of edge dislocation is said to be positive edge dislocation. This is said to be positive edge dislocation. This is said to be positive edge dislocation. So my dear, when it is said to be positive edge dislocation, when it is said to be positive edge dislocation, my dear, what is the meaning of negative edge dislocation? My dear, here atoms are present at top and at the bottom there are vacancies. If the things are going to be opposite, if atoms are present here and vacancy is present at the top, then the same is said to be negative edge dislocation. And my dear, when we are saying negative edge dislocation, Berger vector for that is represented like this. So this is for positive edge dislocation, this is for negative edge dislocation. Because here this line is showing the partial plane of atom. Here this line is showing the partial plane of atom. So my dear, hope you guys are very much clear about the concept I have given you. Any doubt you can please ask me, guys. I am giving you the explanation which never you will find out, never student understand from the textbooks. So I am giving you a brief discussion which is required for your exam. And guys, I will suggest you, if you really want to score good, you can join us in the crash course which is going to be started from Wednesday. And I will be giving you the complete plan for the crash course, where I will be telling you the complete plan for the crash course, which is going to be having all the subject discussion in a great detail. And that will be a crash course which will help you to qualify engineering services paper. Even you will be able to score maximum in the paper 1 there. Yes, Rinkesh, as you can see, the direction of dislocation, you can see these atoms will have a tendency to move like this. The atom will be having a tendency to move like this. So this is going to be the motion of dislocation. Dislocation means the atoms. So atoms are moving like this. Atoms are moving like this. And my dear, this is the dislocation line. So the movement of atoms, the direction of velocity is going to be perpendicular to the dislocation line. Okay. So my dear, this is dislocation line. This is the atom's movement. So it is going to be perpendicular. So that's why I said it is going to be perpendicular. Dear, edge dislocation, I already told you, dislocation means the dislocated group of atoms. It is already mentioned. So group of dislocated atoms is a dislocation. And my dear, why it is said to be edge dislocation? Because it is like an edge. It is like an edge. That's why it is edge dislocation. Dear, this crash course will be starting from Wednesday at 11 AM, the present timing only. And this material science, as I am taking, now we will be converting this into a crash course where we will be discussing all the subjects. Pramila, hello dear. Okay, yes. So dear, this is something known as positive edge dislocation. Okay, positive edge dislocation. So this is positive edge dislocation, this is negative edge dislocation. In negative edge dislocation, here the atoms will be present, here there will be vacancies. Yes. Now my dear, I am showing you another look of this. This is something you can say as edge dislocation. If you see, this is the perfect crystal. But my dear, if you see, here the atoms are not there. So due to that, these atoms get attracted. That's why this got moved like this. Okay. That's why here the movement is there. And because of this movement, here also atoms will move. Why? Because the gap between the atoms have been more, so these will be attracted like this. So this is the movement of atom you can feel here. So my dear, this is another view for the same edge dislocation. Sir, if plane defect in 3D is also called in line defect, and analysis is same or not, or something different from this? Dear, when point defects are coming in more than one, they result in line defect. When line defects are coming in more than one, they result into surface defect. When surface defect are coming into more than one, it becomes volume defect. So this is how the defects leads to each other. This is how they invent each other, they produce each other. So right now we are talking about line defect. When it will be coming in 3 dimension or 2 dimension, it will be changing in the name itself. Obviously there will be a change. Then more than one line dislocation will be present, and that will be converted into tilt boundaries. I will be telling you about that also. So just wait for some time. So my dear, this is said to be edge dislocation. Now please tell me guys, shall we move on to the next type of dislocation known as screw dislocation? Are you getting this? Shall we move on to the next dislocation? So edge dislocation is going to be there in the form of positive edge or negative edge. Here the velocity vector is perpendicular to the dislocation line. This is what I wanted to tell you about that. Yes. Got it guys? Fine Dev. Let us see now the screw dislocation. Now my dear, next we are going to see the screw dislocation. My dear, I am taking an example now. Dear, on this channel only, crash course will be on this channel only. Crash course will be on this channel only. Okay, I will be announcing that in Telegram channel also, and from Wednesday we will be starting that. Dilip Singh, I would like to tell you that for paper 1, for different subject, different books are there. I will suggest you don't go for any book. We are also launching a practice session series for paper 1. So guys, whatever we are thinking of, basically at none of the platforms students are getting the proper content for paper 1. So that's why we have planned it for you guys. We will be providing you a practice session for each subject, as well as we will be providing you the PDFs of the practice session on the Telegram channel. Even on Gradeup app, I am going to take some special series of paper 1. Like in March, from 7th or 8th March, I am taking a practice series over project management subject. So every subject I will be taking that practice series over Gradeup app as well as on YouTube. So you just be with us. You need not to go for anything else. And my dear, still if you want, on Wednesday in the first session, I will be sharing the complete list of books for all the subjects. If you want to refer, you can go for that. Sajal, for GATE crash course are there after September, because crash course is a short-term course that we have already run for GATE 2021. For 2022, we will be starting in September month. Yes, screw dislocation, my dear. So when we are talking about screw dislocation, my dear, it is slightly difficult, and my dear, it is difficult to understand as well. So that's why I am showing you it with some example, which is very simple example, but it will give you the clear picture. It is not the exact example of screw dislocation, but it will give you a clear picture of the screw dislocation. Okay, let us say, my dear, we are having a complete metal structure, complete material, complete lattice is there, and from that, let us say I am having this to be a complete material crystal lattice. What I am doing, I am taking a glass and just putting the glass over it and applying the forces into that, so that this book will be cutting in the form of a glass. So I will be getting a cylindrical object like this. So when the glass will be forcing the book will be giving me one part as this, because it will be cutted into this part. So my dear, this will be the part I will be getting. Just imagine it that it is a complete material I am having. I have taken a glass, I have put it the glass here and applied the forces. So this book is going to cut in the form of cylinder, and that cylinder I have taken out and I am showing that cylinder to you. This is that cylinder. And my dear, every page of this book will be acting as a fiber. Yes, every page of the book will be acting as a fiber. So I will say every page, you can see this, every fiber, this is a fiber, and obviously this can be considered as an atomic plane. So my dear, I can show you various number of atomic planes here. These are the atomic planes here. So my dear, these are the atomic planes. All these are the atomic planes, my dear. So all these are the atomic planes. Why I am saying atomic planes? Because on this plane a number of atoms are present. On this plane a number of atoms are present. So my dear, these planes are said to be the atomic planes. So on these planes a number of atoms are present. So I am saying them to be atomic planes. So my dear, this is atomic plane, this is atomic plane, this is atomic plane. Likewise, infinite number of atomic planes is there. If you want to understand screw dislocation, I am telling you. Let us say you are a person standing on this. If you will be going for one complete rotation, don't you feel after one complete rotation you will reach to your original position? Yes, you will definitely be reaching to. You will definitely be reaching to. You will be definitely be reaching to. So my dear, now what I have done, I am applying some shear forces onto this. I am applying some shear forces onto this. So when I will be applying the shear forces onto this, like this, like this, like this. So my dear, some shear distortion, shear deformation will take place. So when I have applied the forces like this was converted in the surface of helix. This was converted in the surface of helix like this. So my dear, initially it was like this. This is the initial case, this is the final case. So in the initial case, if you are starting a journey from here, after one complete rotation, you were reaching at the same place. Okay, but my dear, when we have applied the shear distortion here, after getting shear distortion, it will be taking this format, my dear. And when this will be taking this format, my dear, now if you are the person standing here, now if you will be going for one complete rotation, you will not be reaching at your original position, you will be going slightly downward. After one more rotation, you will go downward. After one more rotation, you will go downward. This is going to be the motion of yours. And if you really feel, initially the atomic plane was like this. Now when the atomic plane is going to be distorted like this, obviously the atoms which are present here, they have moved in this direction. That's why my dear, this complete structure was distorted like this. So the atomic planes have distorted. Atomic planes have been distorted. So my dear, the atoms have moved towards downward. So if I ask you now, what do you feel? Are you getting that this is going to be the direction of atomic movement? Do you feel that this is the direction where atomic planes or atoms are going to move? Where atomic planes or the group of atoms are moved? Or can we say this is the direction of dislocation movement? Can we say this is the direction of dislocation movement? Yes, guys. Can we say this is the direction of dislocation movement? Yes. Yes. Yes, guys. Are you getting it or not? This is the direction of dislocation movement. Now, my dear, I would like to say that when we are talking about the atomic planes, when we are talking about the planes of atom, my dear, this is one plane, second plane, third plane, four planes. All these are the planes of atom. How you will define the dislocation line? Dislocation line is the line which separates the slipped part and unslipped part. So my dear, here if you consider, as you have started from here, it is also starting from here. It was initially like this, but this part is going down. So starting point was previously this one, now also starting point is this one. So I will say this left hand side part can be considered as unslipped part. Left hand side part can be considered as unslipped part. And my dear, at the same time, this right hand side part is said to be slipped part. So my dear, if this is slipped part, this is unslipped part, I feel that, I have a strong feel that this is the line which separates the slipped and unslipped part. So this line is said to be dislocation line. This line is said to be dislocation line. So my dear, dislocation line is something. This, yes, dear. Okay, Dilip. So as I said, my dear, this line is said to be dislocation line because it is separating unslipped part and slipped part. This is unslipped part, slipped part. My dear Dilip, this class is exclusively going on Gradeup YouTube channel for you guys only. Saugata sir, why spiral path didn't get? Dear, it is similar that if you are having a cylinder, you are applying the forces like that. Like if this is a book, if I am going to apply the forces like that, don't you feel this will be getting distorted? Don't you feel this will be getting distorted? So like if it is rectangular, it will be distorted into some rhombus. But when it is cylindrical, it will be distorted in a form of spiral shape, obviously. Okay, because one part will going down, then obviously it will become spiral. Okay, so just have the point I wanted to tell you. My dear, I wanted to tell you that this is the dislocation line and this is the direction of dislocation movement. What do you feel? Here the direction of dislocation movement is parallel to dislocation line or perpendicular to dislocation line. Is it parallel to dislocation line or perpendicular to dislocation line? Okay, please tell me that. The motion of this dislocation is parallel to dislocation line or perpendicular to dislocation line. Please tell me that. So dear, when you will be having a cylindrical surface, when you will be applying the shear distortion, then obviously because of this shear distortion, this part will be shifted to downward. So obviously this will be taking a form of spiral. Yes, it is parallel linkage aksha, very good. Yes, this time the direction of dislocation movement is parallel to the dislocation line. So dislocation movement is parallel to dislocation line. So my dear, this is how they will be asking you the question. So they will be asking you the question in this way. So you will be saying that dislocation movement is going to be perpendicular to the dislocation line in case of edge dislocation, parallel to the dislocation line in case of screw dislocation. Sir, if I apply the force on both the side, the shape will be changed. So how to get unslipped part? Dear Dev, whenever we are applying the force, we do not apply the forces at two parts. Like whenever you are having a member, it is going to be fixed from one side. So whenever you will be applying some load, it will be going to be distorted from other part, but this part will remain the fixed always. Okay, because whenever you apply some forces on some body, it is in equilibrium with the help of some support. So support will be keeping this part to be fixed only. So this is our assumption that every time we are having the body to be in equilibrium because of that. Sure dear Akshat, I will be solving all the previous year's ESE question. Even in night 11 PM I am solving it for strength of material these days. Rikesh sir, इतने सब होता है मुझे आज पता चला. Okay, fine dear. So now I feel you got it that the movement of dislocation is perpendicular to the dislocation line in case of edge dislocation. It is parallel to dislocation line in case of screw dislocation. Okay. Okay, yes. So guys, when we are talking about this is something related to this one. And now my question to you is, previously in the case of edge dislocation, there was a group of atom, 3, 4, 5 atoms were moving, which was said to be edge dislocation. So whenever a group of 3 to 4 atoms is moving, it is said to be edge dislocation. But here, don't you feel, when we are talking about the atomic plane, this complete plane will be filled of lakhs, crores of atoms. So when this plane is going to be distorted like this, then a group of atom is not of 5, 6 atoms. It will be thousands of atoms which are going to be distorted. So don't you feel here bulk motion of atom is going to take place. whereas in edge dislocation only 5-7 atoms were moving. So in screw dislocation bulk motion is there. In edge dislocation the motion was of certain group of atoms. So don't you feel that screw dislocation is something which require more energy because a bulk of atom is going to move. So my dear, don't you feel that whenever we are talking about edge and screw dislocation, then screw dislocation require more energy than edge dislocation? Please tell me that, because any kind of distortion requires some energy. So edge dislocation only 5-6 atoms were moving. Here complete plane is moving. So don't you feel here more energy is required to move the complete plane? Don't you feel that? Please tell me that. Yes. Guys, please answer. Otherwise you will not get. If you want to get all the things from your inside, you need to answer me. I am just solving the question of previous years in front of you without showing you the questions. Okay. So I will be showing you the question also in the next class. Okay. So that you can know what are the things asked. So my question to you is, don't you feel there is a bulk motion in screw dislocation as compared to the edge dislocation, which requires more energy? Yes. So my dear, my question to you is, energy for the movement, if it is going to be taken from temperature, what do you feel? Which defect will be coming at higher temperature and which defect will be coming at lower temperature? What is your feeling about this? Which defect will be coming at higher temperature and which defect will be coming at lower temperature? What is your feel about that? Which defect will be there at higher temperature and which defect will be there at lower temperature? This is my question to you guys. And I want all of you to answer this. Which is going to be at higher temperature, which is going to be at lower temperature? Yes, guys. Yes. Yes, guys. Which dislocation at higher, which dislocation at lower temperature? Edge dislocation at lower. Yes, guys. This is the answer to this question. Edge dislocation will be occurring at lower temperature. Screw dislocation will be occurring at higher temperature. Yes. Very good. So my dear, that's what I wanted to say here. And if you want to see the dislocations, this is the example of screw dislocation. You can see this. You can see this as I shown. Okay. Yes. So my dear, screw dislocation, this is edge dislocation. You can see the atom group is absent. Screw dislocation at high temperature. Edge dislocation at lower temperature. Is it fine, guys? Is it fine, guys? Dear, it is good. It is good. But that depends what gate score you are getting. If you are getting very good gate score, then obviously you can get better than that. If you are getting average score, then it is good. Yes. So my dear, next, this is again a figure for edge dislocation. You can see this is the partial plane of atom. This is the closely packed plane. This is positive edge dislocation. Okay. Is it fine, guys? Yes. And this is the screw dislocation, a proper figure. This is the real figure of screw dislocation. You can feel like it is like I have taken some body and twisted like this. So I have taken some body and twisted like this. You can feel it. Okay, this is something, the diagram for screw dislocation. So this is screw dislocation. Yes. Is it fine, guys, now? Yes. So my dear, these are the line defects. Now we will enter into the surface defects. Now we will enter into the surface defects. And my dear, surface defects are classified like this. The very first is grain boundaries. Then there is tilt boundaries, or you can say low angle boundaries. It is divided into two parts: low angle tilt boundaries, low angle twist boundaries. Low angle tilt boundaries, low angle twist boundaries. And my dear, after that there is one more defect. It is said to be twin boundaries. And then after grain boundaries, low angle boundaries, twin boundaries, the last one is going to be staking fault. And my dear, with this chapter will be over, because whenever we are talking about volume defects are not the part of material science. Volume defects are something related to casting defect, they are something related to welding defect, they are something related to forming defect. So these things are the core part of mechanical engineering production part. So that you need not to go for. So we need to complete only the surface defect, and with that your chapter will be over. And I can assure you 2 questions from this, because every year 2 questions are coming from this chapter. Hope you guys are getting it wonderfully. So please tell me, are you getting it? Now we are going to see these defects, and in these 4, this is going to be the most important one. This is going to be the most important one for your examination. So my dear, characteristics of grain boundaries are asked in the paper. रिंकेश सर फिगर से भी क्वेश्चन नहीं डियर, फिगर मैंने सिर्फ इसलिए दिखाए क्योंकि स्टूडेंट्स को एक फीलिंग देने के लिए। जब मैं फिगर नहीं दिखाता हूं तो स्टूडेंट बोलते हैं सर फील नहीं हुआ कि क्या हो रहा है। स्क्रू डिस्लोकेशन को फील करना थोड़ा मुश्किल है। और आप एक चीज देख सकते हो, यू कैन सी वन थिंग, दिस फिगर आई कैन नॉट मेक मैनुअली because it is a 3-dimensional figure. So that's why I show these figures. Otherwise, if you understand by my manual diagrams, not better than that anything can be. Because for understanding, my diagrams are much better than these diagrams. But practically, when you see animation part, then this is the reality. So you must know the reality as well. Okay? Yes, guys. So now let us see the surface defect. The very first one we are going to discuss is grain boundaries. Grain boundaries. So this diagram is taken from the Gradeup study material only, okay, which is already there with the students of Gradeup. So my dear, when I am talking about the grain boundary, so my dear, let us see what is grain boundary, and today you will be getting clear about grains as well. What is grain and grain boundary? Let us see in a great detail. So my dear, let us say I am having a container, and my dear, in this container some molten metal is there. During casting you will be having some molten metal. This is the molten metal you will be having. It is similar to, my dear, whenever you have a bowl filled of water, you put it into refrigerator for making the ice. It is similar to that. Dear, from this topic only conceptual question, but from crystal structure numerical can also come. Okay, this is the second chapter going on Sajal, and you missed the first chapter. In the first chapter, numericals are coming. In first chapter, concept plus numerical. In second, only concept. Okay. So yes, because here numericals are not there. So how they will ask numerical? They are just the conceptual points. And they will be the points like at higher temperature which defect is there, at lower temperature which defect is there. Okay, vacancy, self-interstitiality together will give you Frankel, Schottky, which defect. That kind of questions are coming. So my dear, when we are going to say what is grain boundary, dear, I am having a liquid molten metal in a container. This is molten metal in a container. My dear, we are having the molten metal in a container. Okay. So what happened is, these are the walls of the containers, and walls of the container are generally colder. So when you are going to put a bowl in the refrigerator for making the ice, Aditya sir, please come live with these lectures on mechanical marbles, as it is easy to find. Get notification related to mechanical engineering. Okay Aditya, don't worry. Actually, this is paper 1 common for all the branches. That's why we are coming on Gradeup YouTube channel. As this is common channel for all the branches. That's why. Otherwise, all mechanical related specific lectures are on mechanical marvels. Don't worry about that. Okay. If you join our Telegram channel, every notification you will get. So my dear, when we are talking about grain boundary, my dear, whenever you are going to put the bowl of water in the refrigerator so that the ice can form. So my dear, when you put it, basically what happened is, you know, sometimes when electricity gone in between, you take the bowl out, you find out the water is there at the center. From sideways berth, the ice is already made. In center you will find the water. Why it is so? Because my dear, solidification fronts are always coming from the walls of the container. So when the solidification front will be coming from the container, ice formation will be taking place in this direction. Ice formation will be taking place in this direction. So that's what I am saying, that solidification front will be starting from this. What is solidification front? It is nothing but, my dear, the solidification will be starting. It is nothing but like unit cell will be solidifying in this direction. Here unit cell will be solidifying in this direction. Unit cell will be solidifying in this direction. And this direction is nothing but a grain orientation. And here the atoms are, here the crystal are solidifying like this. Here crystal solidifying like this. Here crystal solidifying like this. So in this way crystals are solidifying from the walls everywhere, solidification fronts are coming. From the walls everywhere solidification fronts are coming. And my dear, when these solidification fronts will meet, my dear, the complete material you will be getting. And the complete material, when you will see, you will be getting this kind of shape. So what happened is, this is said to be a grain after solidification. After solidification, it is a grain which is having a specific grain orientation. Now, wherever, like let us say many grains are growing. So whenever you are going to have, let us say this is one grain, this is another grain, another grain, another grain. So the place where two grains are meeting, this is grain number 1, this is grain number 2. So this is a grain boundary. This is grain number 3, this is a grain boundary. This is grain number 4, this is a grain boundary. This is grain number 5, this is a grain boundary. So my dear, grain boundary is something which separate two grains, which is the combination of two grains. It is like a boundary between two states. It is like a boundary between two countries. It is like a boundary between two cities. It is like a boundary between two places. That is said to be grain boundary. And every grain have different grain orientation. Like whenever I am teaching, I am telling you this is a grain with this orientation. 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 So my dear, these are the grains with different orientations. Okay guys, so these are the grains with different orientations, and wherever two grains meet with each other, it is said to be a grain boundary. And my dear, when we are going to discuss about grain boundary, here we are going to discuss the characteristic. Okay, so the characteristics of grain boundaries are similar to that of characteristics of any boundary. I am telling you how. Characteristics of grain boundary. This is the important part for your examination. My dear, let us say you are having two states of India, like I am saying Rajasthan and Gujarat. As you know, Rajasthan is there, Gujarat is there, these are two states. Obviously, there is a boundary between Rajasthan and Gujarat. So, my dear, that boundary is like Rajasthan is a kind of grain, Gujarat is a kind of grain. The boundary between both of two will be acting like grain boundary. Let us take some example. If I am talking about the boundary which is there between Rajasthan and Gujarat, don't you feel at that boundary both the people belong to Rajasthan and the people belong to Gujarat, both will be living there. Let us say Rajasthan peoples are using Marwadi language and Gujarat peoples are using Gujarati language. At the boundary you will be getting the people from both the orientations. Similar to that, if you go to the nearby like border of the Nepal and India near to Gorakhpur side, there you will find at the border peoples from both the countries are living there. So at the boundary you will get the orientation of both the sides. You will get the peoples who are speaking in Hindi, you will get the peoples who are speaking in Nepali. So my dear, similar to that, at boundary of Gujarat and Rajasthan, you will get the people who are speaking in Gujarati and the peoples who are speaking in Rajasthani. So my dear, similar to that, at grain boundary, you will be getting the grain of both the orientation, because boundary is made up of two types of grains. So both type of orientations of crystal you will get there. So I will say grain boundaries are the region of orientation mismatch. Grain boundaries are the region of orientation mismatch. So grain boundaries are the region of orientation mismatch. Yes, my dear, they are the region of orientation mismatch. Okay? Yes. So my dear, this is the first thing. My dear, second part, let us see. My dear, as you know that wherever boundaries are there, every time whatever the situation of war is there, that is at the boundary. Like India-Pakistan border, there is a state of war. India-China border, there is a state of war. Means always there will be compressive influence. Why? Because every country want to extend its ranges. Every country want to extend its line of control. So my dear, every country like India wants, Pakistan wants, if both will want, there will be a compressive influence. Likewise, if two states are there, every kingdom wants to expand. So my dear, yes, in India our things are relatively different than others, but still I am taking generally, every kingdom wants to extend its limits. So because of that, wherever two kingdom meets, there is always a compressive influence, because both wanted to enter into the boundaries of each other. So my dear, I will say grain boundaries are regions of compressive influence, and compressive influence when will be there, the gap between the atoms will be reducing from the bond length distance. So there will be instability, there will be energy associated with that. So I will say it is the region of high energy. It is the region of high energy because of compressive influence. Let us see the third point. My dear, I want to tell you that there is a term known as Ghuspat. Like some immigrant peoples are entering. Ghuspat, like we say, a word is used, Ghuspat. Like you have listened many times from many people that from the border of Bangladesh and Bangladesh and India, some peoples are entering illegally. So illegally, the entered migrants, they are said to be illegal migrants. So those are entering from the border. So I will say that all the impurities concentration are possible only at the boundaries, because at boundaries the peoples of different orientations are there. So we may not know which people are coming and which people are ours, which people are not ours. Like whenever you go to a family function where some birthday party is there, so in your birthday party you will be knowing each and every person, because everyone will be your relative. But if you are going to a marriage, let us say your marriage is there, so in your marriage there are people from two families, One is from the boy family, other are from the girl family. So if you don't know every person from the girl family, you may not be identifying which person is yours, which person is theirs. So my dear, that is the condition with the boundary. At boundary, both orientation peoples are there. So every time we are not sure that these peoples are mine or not, these peoples are ours or not. Okay. So that's why, because of that, there are high chances of impurity concentration. That is the reason why in marriages some people go without invitation. But in birthday party, it is not like that. In BTech, everybody of you have seen that thing in 3 Idiot movie, that those three were going to a marriage without invitation. Similar to that, you also have gone sometime, I also have gone sometime during my BTech, that we went to a marriage without invitation. But my dear, we never go to a birthday party without invitation, because we know they will be recognizing us. In case of marriage, they will not be able to recognize you, because boy family may feel you are from girl, girl family may feel you are from boy family. So nobody will ask you there. Okay, I don't know whether you are correlating the things or not, but I am giving you some realistic example which are very easy to understand. Yes guys, so grain boundaries are the region of Grain boundaries are the regions of high impurity concentration. Okay guys, these are the region of high impurity concentration. And my dear, at the same time, when grain boundaries are the region of high energy, now to my dear, melt the grain boundaries, very less energy is required. You know, to melt anything, some energy is required. Let us say if somebody is having 10 joule of energy, other body is having 50 joule of energy, and to melt both of them 100 joules are required. So grain boundary require lesser energy. So my dear, that's why grain boundaries are regions of low melting point temperatures. So that's why, my dear, grain boundaries are the regions of low melting point temperature. Dear Sajal, every person do this kind of thing when they are in colleges, because in colleges, obviously, when we went somewhere outside, basically everybody have these kind of things in the childhood, definitely, because we are not mature at that time. So that is because of that immaturity we do these kind of things. But yes, there is a different enjoyment in these things also. Everything have its own time in life, and we shall go for everything, yes, as per the time. Yes. So my dear, these are the grain boundary characteristics, and hope you guys are getting these characteristics. Now my dear, I would like to tell you that as grain boundaries are the region of low melting point temperature. So my dear, every time at high temperatures, grain boundaries will become soft. So at high temperature, failure will be there from grain boundaries. But my dear, at low temperature, when we are talking about, at low temperature, as you know that grain boundaries are the region of high energy, they are having compressive influence, so they will not allow the dislocation to move from the boundaries. So definitely at low temperature, failure occurs through the grain. So at high temperature, grains are stronger. At low temperature, grain boundaries are stronger. At high temperature, grains are stronger. At low temperature, grain boundaries are stronger. So depending on temperature is high or low, the failure will occur. Hope you guys are enjoying the lecture, my dear. So please like, share and subscribe. In 1 hour, I said this thing only once. Okay. Yes, this you can see the grain boundary. Like this is one orientation, this is another orientation. So my dear, different orientation. This is one orientation of crystal going on. This is another orientation of crystal going on. Some third orientation is coming. So this is the example of grain boundary. Okay, you will always be having compressive influence at the grain boundary. So this is the boundary you can see. Here this is the boundary you can see. Okay guys, so these are the grain boundaries. Now I am coming on to the low angle boundaries. So my dear, these are the low angle boundaries. Like how they are framing, I am showing you. Like let us say my dear, we are having a crystal lattice like this. Let us say we are having a crystal lattice like this. Here if you see, if you try to feel here, if you try to feel here, there is the edge dislocation. There is the edge dislocation. So there are three edge dislocation occurring together. Three edge dislocation occurring together. Yes dear, definitely Rinkesh. Yes, fine. So my dear, as I said, these are the three edge dislocation. So when three edge dislocation will be occurring together, edge dislocation is a line defect. They will result into the surface defect. So what will happen my dear? You can see when this atom is not there. So these two atoms will be far away from each other. Attraction will be there. Here also attraction will be there. And here the gap is far away. Attraction will still be more. Attraction will still be more. Attraction will still be more. And because of that, this will be tilted like this. And you can see it is starting from here and it is tilted like this. And after tilting, it is making an angle theta. So this theta is said to be low angle and it is said to be tilt boundaries. So my dear, low angle tilt boundary defect is coming when more than one edge dislocation is present together. And my dear, similar to that, if more than one screw dislocation will be occurring together, it is going to be result into the low angle twist boundaries. So my dear, these are said to be the low angle boundaries. These are said to be the low angle boundaries. So these are the low angle boundaries. One is said to be the low angle tilt boundaries. Second is said to be the low angle twist boundaries. Okay, these are the examples of low angle tilt and twist boundaries, guys. Okay, yes, fine, guys. So now we are coming to the next one, that is twin boundaries. So my dear, what happened is previously we are having a perfect crystal lattice like this, line lattice like this. Yes. So this is 1, 2, 3, 4. 1, 2, 3, 4. So my dear, this was the case. You applied shear distortion. After applying shear distortion, this will be distorted like this. This will be distorted like this. Let us say this get distorted like this. So previously the structure was red one. Finally it became the structure with black one. So this part remain unslipped. This part is slipped. And these are the two boundaries which are separating this unslipped part and slip part. And this slip part is the mirror image of unslipped part. Slip part is the mirror image of unslipped part. So slip part is the mirror image of unslipped part. So my dear, slipped part is the mirror image of unslipped part. And because of this, my dear, when you will be applying this force like this is going to be slipped part, this is going to be unslipped part. And these two parts are like this. So it is going to be mirror image of slipped part. And my dear, these two boundaries are said to be twin boundaries. And this is shown like this. This is the defect known as twin boundaries. So my dear, why this is a defect? Because whenever this kind of thing occurs, the gap between the atoms which was A is converted into this one, the gap will increase. So obviously because of that, instability will be there. Fine. Yes guys, wonderful. So this is something twin boundaries. And my dear, with that we have seen all the crystal defects also. Now I am showing you the last one, that is the last one is the staking fault. So my dear, to understand staking fault, you must understand the staking sequence. Staking sequence is the orientation of atomic planes, how they are oriented in space. I am showing you how. If you see this simple cubic structure, guys, you know every corner atom is having an atom. Every corner is having an atom. So this is a kind of atomic plane. I am giving the name A to this. So this is again the similar plane. I will say A. So when you will be having simple cubic structure, the staking sequence will be A. Every plane will be of same type. Okay, but my dear, if you are going to see the BCC structure, when you are going to see the BCC structure, in the BCC structure, we will be having all corner atoms and one body center atom. So my dear, one plane is this one which is having corner atom, it is A. Another plane is this one which is having body center atom is B. Then once again it is the same plane, it is A. So for BCC, staking sequence is AB. Similarly, when you will be finding for FCC it will be coming out to be ABC. You need not to go into that how you will get ABC. And similarly, this is for FCC, this is for BCC, this is for simple cubic, and for hexagonal closed pack it will be AB again. So my dear, these are said to be staking fault, how the atomic planes are oriented. But my dear, if this sequence is not going to be followed, then it is said to be staking fault. So staking fault means if the sequence is not going to be followed. So when the sequence will not be followed, it is said to be staking fault. So my dear, if I ask you in which of the structure you will never get the staking fault, it is simple cubic, because it is only one type of plane. Here staking fault may come if B disappears. Here staking fault may come if any of the atomic plane disappears. So my dear, but staking fault will not be there in the simple cubic structure. So with this, my dear, we have completed all the defects and we have completed crystal structure and crystal defect. These two are the highest weighted topic of paper 1. And my dear, hope you are getting in a wonderful way. This is from material science paper 1, the highest weighted topics we have covered. So my dear, for next notification, I will be putting short videos over Telegram channel, and how now the crash course is going to be there, we will be informing you, and you please come regular, then only you will be properly benefited from that crash course. So please tell me guys, till this point, everything you got it or not. Then we are leaving this session here, and thanks for joining and for your love and support guys, and we will be meeting in the next session soon. Okay guys, hope you are getting it in a wonderful, nice manner. So goodbye guys for this session. Once again, thanks for joining. Okay, so goodbye guys, and please before leaving, like, share and subscribe so that it can reach to maximum students. Goodbye guys.